All right. Hello, everyone. How are we doing? Can you hear me? Okay, good. Good to hear. All right, so let's see. Let's start the class. We are in the AVL trees part of the class. Any questions before I start? Any questions about the homework? Okay.
Wait, Professor. Yeah, I had one super basic question. So
yes.
in the homework, when it says for the big five, just use the default. The idea is we don't put our own implementation there, right? Because the
yes.
Okay, cool.
Yes, you can say E equals default. Like you can yeah. So basically, it's best to say equals default.
Okay.
I mean, so that you know that you're using the default. But if you omit the default, you know, implementation is gonna be created. But you know, I think it's best to use equals default. I think you should do that. You know what I mean by that, right?
Yeah.
Yes. So right. Right. So we all right. Sounds good. Any other question? Raise hand. Another question, Guy.
Thank you. When it comes to splitting the elements of the rebase database, you know, with the restriction enzyme and then the bits of DNA separated by slashes.
Right. Yes.
Do you have any advice for that? I've looked around at splitting on C++, and you know, there's not a magical split operator.
You can use string stream. That's something you can use, and basically you can use the slash as the splitting character. So that's like a library, string stream library. Or you can just, you know, you get it as a, you know, you can read it as a string, the whole line. That's the way you should think about it, right? You read line by line, and this line is a string. You can parse it on your own. You can start from the beginning of the string and then character by character, and then when you reach a slash, then you say, you know, it's the separator. So you can write your own thing, or you can use the string stream, you know, class library. You know, this is the string stream from C++ in order to do that.
Okay, thank you.
Okay. Any other question?
Yeah, I have one question.
Yeah.
There are many ways to write the functions that will succeed in like part 2, where you ask for, you know, output of the number of recursive calls and things like that. Do our functions need to return a specific thing, or as long as our output is the same as your output, it'll work on grade scope?
Yes. So basically, the grade scope just checks to see whether this output is the same. It wouldn't look into your implementation. That's gonna just look at the output.
All right. So our functions don't need to return a specific type or anything?
No.
All right. Fantastic. Thank you.
Yeah. But you have to see out, right? You just see out the result. So that's it. You have to see out the result on the terminal, and then, you know, in the way that has been described. And then, you know, grade scope, the only thing it does is just, you know, takes the code. In this case, it may split your main, remove your main, but it's going to call this function that we have test tree or query trees. That's why I told you not to change this, the signature of the function. But, you know, in this your test tree or query tree function, you should see out the output, and grade scope, the only thing it does is just compares the outputs. Yeah, Tom.
Yeah, can you hear me okay?
Yes.
Okay. I'm going to risk asking about something I should know by now, but I don't know what you mean by default. And if you want to just point me to the right part of the textbook.
Oh, yeah. I will just, let me just go to the slides. I'll just do it now. Thank you for asking.
Okay, thanks. Yeah, thanks.
Yeah. All these are photographs. All right. And just go to the first lecture. Wait. Let me see. Just want to find the slide instead of writing it down because it's already there. Here it is. So you can do things like that. So you can have the signature of the function. You know, what is the zero parameter constructor? What is the copy constructor for your class? What is your you know, assignment operator, move assignment, move constructor, all these things. You can write them, but the only thing you can write, you should write just the signature. So in the case, for instance, sequence map is going to be sequence map, const sequence map, ampersand s equals, but you have to say this is default, right? So you can just write the signatures and you say is equals default, and then the default is going to be used. Does that make any sense?
Yeah, but then what code gets executed?
The default code that C++ is going to provide for you. You don't write any code.
Okay. Wow. Okay. Thanks.
Yes, right. So usually, even if you don't have this line at all, right? For instance, if you don't have this particular signature equals default, then C++ is going around the default anyway. But it's good practice to do that. Okay. Especially for zero parameter constructors for all these things, so that you know that the default is going to be called just at the beginning, just 5 lines, right? Just equals default. And it says here in this slide, you can also delete a functionality. So for example, you can delete the zero parameter constructor, for example, which is like, it's not going to be used at all. If you try to use it, it's going to be an error. I wouldn't advise you would do that, but you may want to not use a constructor, copy constructor, or move constructor at all. Say, I don't want to use it, equals delete. That's meaning that if somebody if you try to compile using, let's say, the copy constructor and it had equals delete, then the program is not going to compile. But you don't have, that's like a point that you shouldn't worry about. We don't want to delete anything. So default. All right. Last question before I go on along. Thank you.
Hi, yeah. For part 1, where we overload the output operator for sequence map, what should the output look like? Yeah,
so basically, just output the whatever is in vector string enzyme acronyms, just one after the other, because it's going to help it, because this is what you're probably is start outputting at the end. And I think, as a matter of fact, we have a test, a unit test in grade scope that tests, and that's what we'd expect with the C out operator. Just the enzyme acronyms one after the other with space between. That's it.
Can I ask a question? So for the constructor for sequence map, so I know that you have 2 constant strings that you have to put as parameters. For the constructor, wouldn't you just add those 2 strings to the enzyme acronyms?
No, the first one, the recognition sequence goes to recognition sequence, and the string an underscore enz underscore acro goes to enzyme acronyms.
Okay.
So basic enzyme acronyms is a vector, contains 1 string.
So then the recognition sequence goes to
recognition sequence.
Okay.
Right, there are 2 parameters in the class. Any other question? All right. Yeah, maybe it was not clear from the assignment, but this is what we mean by that. Yeah.
Could you explain the double rotations?
Yes. So I'm going now. So let's go back to let's start the class, and we'll go. We haven't even talked about single rotation, so we'll go into describing exactly what the homework was about, and describing the AVL trees. So I'll go back to the previous class. I just want to remind you of what an AVL tree is, we call it a balance tree, and the only thing, the balancing condition at each node is that you take the height of the left subtree minus the height of the right subtree, and this height should be either -1, 1, or 0. It cannot be anything other than that. So the two subtrees under each node can have a difference of at most 1 in height. That's what it means. All right. So we went through that in the previous class, and we talked about the minimum number of nodes of an AVL tree of height 8. So I changed the slides a little bit. So I uploaded a new set of slides on Blackboard. But you know, it's approximately the same, but you know, there's some small differences, right? So that's what we described in the previous time, and then in the previous class, and then we said what is the minimum number of nodes of an AVL tree of height 8. So I have a height 8. What is the minimum number of nodes? And we went through and we described this idea. So if you have height to 0, you can have only one node. If you add another node, then you go to height 1, right? If you want to hit height 2, you just, I'm sorry, height 1, S1, then the number of nodes you can have is 2, right? You can add a third node under the root, but then you don't have the minimum number of nodes, right? And if you want to go to height 2, basically the minimum number of nodes is 4. And the idea is very simple. You add a new node here, that's your root. And to the left, you add the AVL tree of height 0, I'm sorry. And to the right, you put the AVL tree of height 1, right? So you see that? And then that's why it's 1 plus S of h minus 1 plus of S of h minus 2. So it's 4. And if you want to go to height 3, again, you add the root. To the left, you add the minimum AVL tree of height 2. I'm sorry, height 1. And to the right, you put the minimum AVL tree of height 2. So that's a recursive way of building up the AVL tree for minimum height. Okay, so this was discussed in the previous class. And because this is related to the, yes.
You just, now you froze for about maybe 5-10 seconds.
Oh, really? Oh, let me check my.
It might have been me though. Let me see.
All right. Okay. All right. Sorry for that.
I heard him okay.
All right. So maybe it's like, yeah, your side. That's all right. Yeah. So this is what what to describe. And then if you write down the equation, S of h equals S of h minus 1 plus S of h minus 2 plus 1. This is basically the Fibonacci sequence. And we know that it's some kind of an exponential. We know that f of n is like approximately a constant to the n. All right. So if you solve that, if instead of S of n you have f of n, you have S of h, and you say S of h is a Fibonacci sequence, and S of h is the mean number of nodes, that is approximately the same as a constant to the h power. So the number of nodes is exponential with respect to the height. And now if you search for if you solve for the height is the logarithm of this. So the height is logarithmic. So that's the important thing here. The height of and actually it can be proven to be exactly that number that we said in the previous class, 1.44 times log of n plus 2 minus 1.328. You don't have to remember it. But essentially, the height of a AVL tree of minimum number of nodes is logarithmic. Okay? That's an example for height 9. And you can see it here to the left, right? You have height 0, height 1, height 2, height 3, right? This is height 4, this is height 5. So basically, if you go here to the root, to the left, you have an AVL tree of height 8, and to the right, you have an AVL tree of height, I'm sorry, to the left, you have an AVL tree of height 7, and to the right, you have an AVL tree of height 8, right? 8 and h minus 1 and h minus 2, and it's the same thing everywhere. I'm going to skip this, but you know what we mean by that. I'm not going to skip, I'm going to go through this. So basically, here, this is the AVL tree of minimum number of nodes for specific height. Here's the AVL tree of the maximum number of nodes for specific height, and the AVL tree of maximum number of nodes for specific height is just a full tree. Okay, so I fill all the levels. That's still an AVL tree, okay, of a specific height. Okay, and then if I add one more node, I will go to a bigger height. So basically, that's the AVL tree, for instance. of maximum number of nodes for height 9, okay? In general, if your height is 8, the number of nodes is 2 to the 8 plus 1 minus 1. That's the maximum number of nodes. And again, the height of this AVL tree of maximum number of nodes for specific height is again logarithmic. So it's always logarithmic, even if you have the smaller number of nodes or the biggest number of nodes, okay, for a specific height, okay? So the height is logarithmic with respect to the number of nodes. So that's why we want to add this point here, because before we're talking about minimum height, minimum number of nodes for specific height. All right, so that was a recap from the previous class. Now, let's go into rotations and basically things that have to do with the practical issues of the AVL tree. And the practical issues have to do with, how do we do insertion? And then we'll talk about deletion or things like that. Of course, how do we do find? How do we try to find an item in the tree? Well, we do a regular find, right? There's nothing special to it. You try to find a node into the tree the way you do it in the banner says tree. But the insertion is different because you want to make sure that the tree after the insertion remains an AVL tree, right? So we'll go through all these cases, right? But what we will, the idea here is that you insert the way you insert in a binary search tree, and then you figure out where you have a violation, and then you fix the violation, okay? So this alpha that you see here is the first node that where we have a violation. Okay, and we'll explain this in more detail. That's just like a overview. So for instance, imagine that you have this AVL tree is already, we start from an empty one to give you the point later, but now this is an AVL tree, all right? And the blue numbers are basically the heights of the nodes, and the red are just the balancing condition, the height of the left minus the height of the right. And this, as you see here, is like perfectly fine, AVL. So let's say you want to insert 4.5. So, okay, so you will insert it here, all right? The same way you would insert it in a binary search tree, 4.5 will go there. And the thing that you have to note is that as you try to insert 4.5, you go to 5, you say it's more than 4.5, then you go to 2, you say 4.5 is greater than 2, then you go to 4, you say 4.5 is greater than 4. It was now there, so you place 4.5 over there, right? Now, the nodes that you follow as you insert, these are the nodes that may change, their heights may change, okay? These are the only nodes. Any other node in your tree, any height in any other node in the tree will not be affected. All right, so even if it has, let's say, millions of nodes to the left or right in the other side or whatever, the heights will be affected only as you insert. Okay, is this clear? And you can see why, right? So let's say, what's the height of 4.5 after you insert it? What's the height of a leaf?
0.
Mm-hmm. So 4.5 will have height 0. What will be the height of 4?
1.
Yes, it's not change. What will be the height of 2? 2, nothing's going to change, right? Because the height of 4 is 1. So, everything above it's going to remain the same. Does it make any sense? You can do the calculations. But essentially, the heights that are going to affect it, they're going to be only on the path to the root in the insertion. In this case, only the height of the leaf was affected. If you try to insert 0, for instance, this AVL tree, it will go all the way to the left. What will be the height of 0?
0.
0. What will be the height of 1?
1.
1. And the height of 2?
2.
It will remain 2, right? Always the height of a node is the height of the left, maximum height left or right, plus 1, okay? So now it's 2, and then nothing will change to going upwards. So that is very powerful thing. That's why the only thing you have to worry about is the path going from the insertion to the root. And then this is where you check for violations, okay? We'll see how. So basically, the only thing you do, you update the heights of the nodes as you go from the insertion point to the root. And then you check for violations. Do you see any violations here as you go back from the bottom to the root? These are the heights. Do you have violation at node 1? Yes or no? Left minus right, is it okay?
Yeah,
Can you
that's,
hear me?
yeah.
Left
that's
minus right.
Negative
Yes,
1 and 1.
it's fine. Yes, at node 2, 1 minus 1, 0. At node 3, 2 minus 1, 1. So there's no violation, okay? So nothing, you do nothing, but there's no violation, right? So essentially what we're talking about is that you address the problem only when there is a violation. So as you go back from the bottom to from the leaf that you inserted to the root, you will stop at the node that you will where there's a violation. If there's no violation, then that's perfectly fine, AVL tree, and you deal with it with rotations, and we will introduce 2 rotations. One's called single, and one is called double. All right, so we'll go through the single rotation first. And that's a single rotation, right? So basically, that's the basic idea of how it will look, and we will explain with examples. So that's a single rotation, a left single rotation. So here the violation, supposedly it happens at K2. So you do a single rotation about K2, a left one. So what happens is you see that what you're doing, you're rearranging the nodes in that way. And then these X, Y, and Z are subtrees under K1 and K2 that are not affected. Again, they may have millions of nodes, but they will not be affected. So the only thing that happens here is you have a K2 and K1, and essentially you rotate them. K1 goes on top and K2 goes to the right. Question?
Yes, can you tell us, or is there a violation here, or are you just saying there?
Now I'm telling you, yes. So we saw a violation, and the way that you see it in this diagram, if you see this X tree, is like the difference between when you're at K2, the difference between the left and the right subtree is 2 levels. If you see these dotted lines, okay, this is just visual.
Thank you.
All right. So basically, and the reason we do it like that essentially is because we inserted something that made this X higher than before, as you see it on the left, and because of that you had a violation. That's the case. It's like you set to the left of K1, and basically it makes it higher than what it used to be before, and because of this structure it will look like that. Okay, and when we correct it, actually there's no problem. At K1 the height now is going to be what it used to be before for K2, and the only thing we have to do is this thing, right? So we'll see how this is done. And basically, the other thing that you have to realize is that nothing will change with respect to the relative order of keys. So for instance, if you see to the left key before the rotation, the left tree, all the nodes on Y, what are the keys on the nodes in 3? I'm sorry, all the nodes on 3X, for instance. They are smaller than K1, right? So if you see at the new tree at the right, all the nodes on the X subtree are smaller than K1 as before. This you have to preserve, otherwise you will not be able to find anything if you just destroy this property, right? Now on the left, all the keys on Y are between K1 and K2. The same thing on the right, all the keys on Y are between K1 and K2. On the left, all the keys on Z are greater than K2. The same thing on the right. So basically, you don't change anything with respect to the relative relations of keys. Okay. And you can do it in the other way. That's the opposite way. That's the single rotation where it's a symmetric way, where basically the right tree becomes bigger, the Z. And again, it's the same idea. Okay. So let's see it with an example. And then, yeah, we also have an applet to see it in more detail. So we see this tree on the left. That is actually, it's an AVL tree as before. Every time you insert, the tree is an AVL tree. So basically there's some kind of insertions. We have this case here on the left. And now we will try to insert 6. All right. So inserting 6 means that 6 is going to go over there, right? Does that make sense? 6 goes over there, and that's the order of insertion. You see these arrows. This is how we went to 6. It was there, 6 greater than 5, 6 smaller than 8, 6 smaller than 7. We put it over there, right? The same way as before. And now we adjust the heights. Okay, so, and we have to go back and check whether we have violation anywhere. Do you see any violation anywhere? We can do it one by one. The height of 6 is 0. What's the height of 7?
1.
1, right? Now, if we're at 7, do we have any violation there? You look under your 7. Is everything okay?
Yes.
Yes. Now we'll go to 8. Now, the height of 8 will be 2. Sorry. But before I adjust the height of 8, I don't want to adjust the height of 8 yet. Under 8, do I have a violation?
Yes,
Yes.
because, yeah.
Because, yes, the left is greater
Left
than the right.
Mhm.
Yes, by 1 minus 2. So essentially, that's the node of violation. Okay, that's your violation node. And now we call this a single rotation. Why? Because the violation happened because we inserted to the left node of 8, and then we insert to the left of the left. Okay, that's why it's a single rotation. Okay, that's how it looks like. So basically, you have the violation node, which is 8, and we have a 7 under it, and you have this X and Y and Z subtrees. Some of them may be null. All right, so this is the case. Okay, you have in this case 8 is K2. I don't know what's the other one. 7 is K1, right? The X contains only 6, and Y and Z are null, right? So what do? You just reverse the order. 7 goes up, 8 goes to the right. It's a left rotation. I don't know if you can see it. And then basically the nodes are being the trees are being adjusted this way, X, Y, and Z. So basically X is 6, Y and Z are empty, and this is your tree. Is this clear?
So basically, in order for there not to be a violation, the tree would have to be basically balanced, is what you're saying.
Yes, I'm saying you're doing exactly this operation.
Okay.
Single rotation. And it doesn't matter what you have between under X, Y, and Z. You have millions of nodes, right? When you see this violation, the only thing you do is that you adjust it in this way. That's one case though, right? We have multiple cases, okay? And if you fix it, then you actually, that's it. You fix it at 8, then you don't have to go upwards. It's done because the height that you have at 7 at this location is the same that we had before. So you don't have to do anything upstairs. So you just do one operation and then it's done. Any question, David? I think you had the question.
Yeah, if Y was not null after the rotation, what would be the relationship between 6 and Y?
Well, if Y was not null, right? Well, Y will be, let's go here. We'll go over there.
So, but right now I see 7 is 7's left node.
But if Y was
6.
not null, that's the question that Y has to be null. If Y was not null, you wouldn't have an AVL tree.
Oh, I understand. Thank you.
Right? If you had something to the right of 7, you wouldn't have an AVL tree to start with. So that's you should have first addressed that. So yes. Any other question?
Well, if you have 7.5,
if you want to add 7.5 now,
or if you had 7, just in the hypothetical case before, if Y was not null,
you mean
but
here?
you would have corrected that before you got to this point.
If you insert 7.5 now, you have to correct it at 8 again, because basically you have violation at 8 as you go back. So when you insert, first you correct and then you insert something else.
Professor, I have a basic question. So when it comes to keeping track of all these heights, is that something that I guess like how are we necessarily doing that again?
Yes, so we didn't go into the code. So
Gotcha.
I'll show you the code, but you keep track of the heights. So each node has a height parameter.
Oh, okay.
So you keep track of it.
That makes
You keep
sense.
track of the heights. So as you see here, and it's going to be, each node has a height, and then like that, you know, the height of the leaf becomes 0. But then when you get the rotation, the heights of the nodes and the rotation may be updated, and we'll see how it's done through the code. And then no other height is going to be changed. Okay. But you know, this is like we will explain that. Okay. All right. So let's try to do 3 to 1, 4, 5, 6, 7 in an applet. All right, 3 to 1. We insert 3. Okay. Now that's the applet. The only problem that we have here, can you see it?
Yeah.
Right. Is like this applet, it just displays the height, but it has a different assumption for the height. So it assumes that height of a node, of a leaf node, is 1 instead of 0. Okay, that's the only difference. Okay, so when you see 1, it's actually 0 based on our assumption. Okay, it's always an assumption, right? We assume that height of node is 0. This guy assumes that the height of a leaf node is 1, but everything is the same. So let's try to insert 2. Right, 2 will go over there. That's easy case. I'm not gonna, you know, that's an easy case. There's no violation. Let's try to insert 1. Okay, so 1 will go there. Now you'll go back and check the heights. Okay, the height of this guy, is there a violation over there? At 2?
No, no.
No. Its height will become 2. Okay, fine. Is there a violation over there?
Yes.
Yes.
Yes. And that's a single rotation. Okay. Why it's a single rotation? Because the violation happened after our insertion to the left of 3, and actually to the left of 3. Okay, that's a single rotation is going to do that. What? You missed that?
I missed that word. A word.
Yes.
After you said violation.
Yes.
Something like rotation.
Yes. I said that the violation happens here, right? Because we set it to the left of the left. Okay, you send to the left of the left, and that's a single rotation. Okay, always. So basically, this is your X, this is your Y sub 3, and this is your Z sub 3. Okay, which are null. Y and Z, they're all null, in fact. Okay.
Okay.
Is this true? Actually, no. I'm sorry, I made a mistake. It's the same as before. This is the X sub 3. This is the Y. We have 3 nodes. Okay. And this is the Z, and Y and Z happen to be empty. Okay, so you do a single rotation the way we know how to do single rotation. And then it says, and basically this is what it is. Okay. All right, so basically, as you see here, this is the X, this is the Y and Z went under here. If you look at the slides about how the rotations are happening, Y and Z actually are empty, and this was the X, and this is what happened. So I think the next insertion is 4. Is this 4? Let me see. 4, 5, 6, 7, right? So 4. It goes there, easy. All right. Now we go back. Violation there? No.
No.
Violation to the root? No. Okay. So 4 was fine. So we try to insert 5. Oh, it went over there. Oh, did already? Oh, step back. Sorry. Let's try to insert 5. Okay, so now let's see what happens. We go back. So forward, sorry. And do we have violation there? No. Do we have violation at 3?
Yes.
Yes. And it's a single rotation again. Why? Because we inserted, sorry, let's do, we inserted to the right of 3 and to the right of 3. This is the case of a single rotation, okay? And then, you know, this is your X. This is your Y. Yes, a question. And this is your Z. I'm listening to the question or not?
Professor, I'm curious. What is why is it a single rotation again? I understand like why you're doing the single rotation, but why is it considered that?
Why we do a single rotation?
Yeah.
Okay, we do a single rotation whenever we have a violation, and the rotation is due to the insertion to the right of the violation node. As much as we insert 5, we insert to the right of the right. You see that? Right of the right.
Mm-hmm.
Violation was at 3. We inserted 5. It was to the right of 3, but also it was to the right of the node under 3. Okay. This when you do a single rotation, right, right, or left, left. This is what we showed before. Okay. Right, right, left, left. Right. So basically, if you do the rotation, of course, 3 and 4 are involved. 4 is going to go to the top, 3 is going to go to the left, and all these things are going to, you know, you can just run it, and, you know, 4, 3, 5. All right. Does that make any sense?
Yeah.
All right. And let's do a last one. Insert 6. Okay, now we inserted it at 5, go back. Do we have violation? No. So we inserted 6, right? Under 5, no violation there. The height of this node 5 increases. Do we have violation over there?
Yes.
No.
No, you don't. Left
No.
and right is like -1, the difference.
Oh.
The height of 4, David, yes, you have a question? Let me finish this. Is there a question for this point? No? Okay. So the height of 4 will increase, right? You see left and right heights are 1 and 2. So basically the height of 4 is going to be the maximum of the 2 plus 1. 3. Now, do you have a violation at 2?
Yes.
Yes. Okay, let's see what type of rotation is that. Okay, we have a violation at 2 over there because the height of the left minus the height of the right is -2. What type of rotation is that? Okay, so what do we insert? We inserted 6, right? This guy here. So we insert it to the right of 2, and then to the right sub 3 of the right of 2. Do you see that? 6 went to the right sub 3 of the right of 2. And if you see the slides, basically, here, the right sub 3 of the right of the violation became higher. I mean, we don't, and then we just have to do a rotation, okay? We don't have to, you know, it's like, all right, so basically, right of 2 is 4, and the right of 4 is where you insert 6. So it's a single rotation again. Now let's talk about the nodes here. So we have a node here, which is K1, right? We have a node here where the violation is happening. If you just follow the slides, we have a node here that's K2, and then we have 3 subtrees, right? We have 3 nodes, 2 nodes, we have 3 subtrees here. This is 1, this is the X. This is the Z. See, now the subtrees are a little bit bigger, they're not empty. I'm sorry, this is the Y. And this is the Z subtree. Does that make any sense? Okay. So how it would look like, let me try to draw it. Okay, so here we get K2 on top. So K2 is 4, right? What will get to the right, to the left? We'll get to the left.
K1.
2.
2.
Yes. All right. Let me just draw now. Then we have 4 and 2 done. So we need 3 more subtrees. Okay. So to the left of 2, we'll get what?
1, which is X.
You get the X. So basically, the X has only 1. Okay. Sorry. Okay. To the right of 2, what will you get?
Y.
Y has only 3, right? Does that make sense?
Mhm.
This total, no, what it says. Okay, and what will get under 4 to the right of 4?
Z.
Z. Yeah, and what is Z? It's just the whole tree that you see there. It's like 5, 6, right? That's making sense? Okay. All right. So this is what it is. So if you do it, oops, let me just stop there.
Hey, but wouldn't you need to add something to the left side of 5?
Some to the left side of 5?
Didn't you need to add something to the left
No,
side?
no. Unless I did unless I did a mistake. If you look at the way it is right now, okay. K1 and K2 are your nodes, 4 and 2. These are the ones that are being put to the top. And then you have 3 subtrees under them, the X, the Y, and the Z. Okay, so this is the X. Sorry, that's the Y subtree. And that is the Z. So if the Z doesn't have anything, whatever, sorry. Right, the Z subtree doesn't have anything to the left. It's 5, 6. That's the left subtree. Just follow. It's like we just use it the way you see it. Okay, you don't have to think about it. Actually, the code will not think about it. It will just do it. Okay. So these are the subtrees, and then you step forward. And then it will do the rotation because, and that's what it looks like. 4, 2, 1, 3, 5, 6, the way we have it on the right. Okay, is this clear? Okay. I clear the drawings. So this is how the tree looks like. Oh, we have to insert 7. Let's insert 7 so we continue finish the example. All right. So we insert 7. What do you think will happen if we insert 7? Is there any violation somewhere?
No.
How about here?
Oh, yeah, you're
okay.
right.
Yes, and but that's a simple rotation the way we did it before, so I'm not gonna go over it. But that's how the tree looks like now. Okay. Now this is the single rotation case, but it fails in this particular example. So if the violation is happening because you insert to the left of the node K2, so you have a violation of K2, you send to the left of K2, but to the right of K1. So this is a left-right insertion. Then if this happens, then you have the single rotation doesn't help you. Okay, all the rotations we were describing was left, left, or right, right. Now the violation happens because we insert to the left of K2, but to the right of K1. Okay, so this is when you get the double rotation, which looks like that. Okay, basically we change the terminology a little bit, but again, the idea is that the violation happens because you, with the example you will see why it's like that. The violation happens because you inserted to the left of K3, but to the right of K1. Okay, so now you see the trees will be like that. Okay, and all of these trees may be empty. A, B, C, and D may be empty. Okay, or not. So the simplest case that we're gonna see is that they're gonna be empty. And then the only thing you do is that you rearrange them in this way. you put the K1, K2, K3 in order from smaller. K1 is the smaller, K2 is the middle, K3 is the larger. And then after that, you attach the subtrees A, B, C, and D under them in that order, in the same order that you had them before. Okay. And you can have the opposite result where you insert to the right of a node and then to the right of K1 and to the left of K2. And you have violation at K1. So if you look at K1 as the violation point, the question is, why did you have the violation? And if you have that, then you do a double rotation, is the right left. There are two cases that are the same, okay? So let's see an example of a double rotation we can do with, continue that like that, 16, 15, okay? So we insert 16 to that tree. So we'll see it happening. So we'll go back. Do we see evaluation here?
No.
No, right? Here, no. Okay. So there's nothing is happening. 16, 15. We said 15. Now you'll see what is gonna happen. Okay. So 15 is fine. How about here at 16? Are we okay?
Yeah.
How about at 7?
No violation.
Violation. Now, why is this a double rotation? Why are we going to do a double rotation here? Because the insertion happens, we inserted 15, we inserted to the right, 7 is our violation point, right? We inserted to the right of our violation point, okay, which is here, but to the left of the right. So it's a right, left, okay? That's a double rotation. And you know, you have these 3 nodes here. Double rotation, you have 3 nodes and you have 4 subtrees, A, B, C, and D, okay? Under 16. Does that make sense? And D, which are all empty, okay? So what do you think is gonna look like after we do the double rotation?
15 where 7 is. And
yeah, so
7 goes
basically
to
15 will be in the middle because it's the bigger, the middle one. And then we will have 7 under it here to the left and 16 to the right. And then you will have 4 subtrees to take under 7 and 16, but they're all empty, A, B, C, D, right? So this is how it's gonna look like, okay? So let me clear everything. Yes?
Just a quick question. Just like, what is the K1, K2, K3 in this example?
Yes, so K1, K2, K3 in this example are these 3 nodes. So let's go back to the slides. It was a right-left violation, right? It was this one, K1, K3, K2. Now the book puts, you know, the way the book uses this notation is like from smaller to larger. K1 is the smallest, K2 is the middle, K3 is the largest. So that's the way they have this notation, 1, 2, 3. Okay, it can be some parameters, but essentially these are the 3. You see K1, K3, K2. They're like exactly what you see here, right? K1, K3, K2. You see that? Yeah. K1 is the smaller, K2 is the middle, K3 is the largest. K1, K2, K3. So and then it's extremely simple rotation. Obviously, it's a double rotation with empty trees. But it's the same, it doesn't matter. These 3 nodes may have millions of nodes under them, the rotation will be exactly the same and with the same complexity. The subtrees under them are not affected, okay? 14, 15, what was the next one? 14, right? After to insert 14, let's see. Now, again, no violation there, insert 14. Do you have a violation here at 15?
No.
No. The height of team is going to change. Do you have violation there? Oops. Oh, let me just step back. Sorry.
Yes.
You have a violation over there. Okay. Why? Because the height of the left minus the height of the right is more than 1. And you see, again, the same type of double rotation. Why? We inserted 14, we said to the right of 6, where is the violation point, but then to the left of 15. Okay? We said to the subtree to the left of 15. And it's the same idea. You have K1, K2, K3 as before. And what are the subtrees that you have? What is subtree A? The one to the left of K1.
Would it be 5?
5.
It's only 5. What is subtree B?
14?
No.
7 and 14.
No. The 3B is basically to the left of 7.
Oh, so
Also,
nothing.
it's empty?
Empty. Subtree C is
14.
That's the order. And subtree D is 16. Okay, so you have these 3 nodes that go from 6, 15, 7, and then you have the 4 subtrees A, B, C, D, and then you just do the rotation. Okay, 7, 6, 15, they go in their natural order. To the left of 6 is A, to the right of 6 is B, that was empty. To the left of 15 is 14, and to the right of 15 is 16. Okay. All right, let me just. Okay, let's insert 13. Maybe I think you get the point of how this is done. Okay, do you have violation there? No. Do you have violation here? No.
No.
How about here?
Yes.
We have violation. We said it's 13. Okay, and again, we said to the right of 7. Oh, sorry, let's go back. Now, why do we do a single rotation here? Not a double. We said it's 13. The violation was at 4. Why is it a single rotation?
Because we went left twice.
Yes, we said 13 is to the left of 7, to the left subtree of 7. Okay, so it's I'm sorry, to the right subtree of 7. So it's right of 4 and right of 7. So basically, it's a very simple rotation, and the subtrees are. That's the first one, the X in the single rotation. That's the second one, the Y, and that's the third one, the Z. Okay, so the only thing you will do, you put 7 to the top, 4 to the right, to its left, and then the subtrees will follow. Okay.
So may I?
Yeah.
I'm sorry, could you go back?
I'll go back.
Thank you. So it's a single rotation because we went right twice from
Yes.
to 7, then to 15, or
this is the tree before the rotations. We said the insertion was 13. Okay, the violation is happening after we go back all the way. It happens to be at the root. Okay, this is where the violation is happening here. Okay, at the root. Okay, so we insert 13. Where is 13 with respect to 4? It's to the right of 4 and it's to the right of 7. So if you see the single rotations cases, it's here at the top. Okay, you see all of the cases. If you see the second single rotation case, the violation happens because you insert to the right of K1 and to the right of K2. Okay, right. Is this clear? This 13 was inserted at the subtree to the right of 7 and 7 to the right of 4. So as you go back in the violation, just go back. Right, you insert it here to the 13, right? Now, you check, there's nothing is happening, you go to 7. Of course, you know that 13 is to the right of 7, that's the right subtree. And then you know that 7 is to the right of 4. So the right, insertion. So you go to the single rotation. Okay, and the single rotation is very simple. 7 and 4 and right, 4 and 7. 7 will go to the top, and 4 will go to the left, and all the other subtrees are going to be the ways before. Okay.
Could you please go forward again? I just want to see what happens to 6 and 5.
I cannot do it. That's done. Oh, sorry. 14 now. 15. No. I don't think I can go back. I think it's destroyed now. Do you see 14
Okay.
anywhere?
Thank you.
Yeah. Yeah. Okay. Sorry. I will insert 15 really fast. Okay. And then I insert 13 really fast. Okay. Okay. And that's what happens. This is what will happen. Okay. So when we said 13, this was the situation, and this is when we step forward, we go back like that. Okay. Fine.
It looks like
Okay,
quite a
yes.
bit of juggling.
No.
No?
Nothing. It's extremely simple. There's nothing that happened here. Oh, I did the same thing. It's like, it's nothing really. Oh, wait. Okay. I'll do it again for the 10th time.
Professor, quick question.
Okay, see, there's nothing really. The juggling is like nothing. Really. Here, okay? What is the juggling? Nothing. 4 and 7. 7 goes to the top, 4 goes to the left, and all the other subtrees are basically not affected. Okay?
Oh, no, 6 and 5 had to move over to 4, and then
Yes.
5 went below 6.
Yes, so exactly. So this is it. This is it. Yes. X, Y, and Z are subtrees that are just going to different locations, but they're not actually moving at all. The pointers from K1 and K2 are the things that are moving. X and Y and Z, basically, they are where they were in the memory. We just visually we sit in a different location. Okay. Any other question before I move ahead?
Quick one.
Yeah.
When we see a violation, especially with that last violation, we went to the left of 15 twice, but we don't need to look at that because the violation happened at the root, and we'll only look at two. We'll only look at 2 movements past that, and so that's how we knew it was right, and so we'd only do a single rotation.
Yes.
I understand. Thank you.
Yes. So if we continue, we'll do 12. Just maybe we should do everything so we get a better idea. Now we said 12. What do you think will happen? Any violation anywhere?
So that's a right-left violation. So you'd have to do a double.
No, see that now the violation was happening at 14, right? It's a violation at 14. You see the left minus the right. You know, it's like the left is like twice. Is minus 2. But why? The only thing you have to ask yourself is why I have violation. I inserted 12. I set it to the left of 14 and to the left of 13. Left. It's just a single rotation. Okay.
3 minus 1
the violation.
is 3 minus 1 is 2, so there's a violation there, right?
Yes. So the violation is at 14 because we said to the left of 13, to the left of 14, I'm sorry, and then to the left of 13. So it's basically left. Yes. Question. Okay. So that's a single rotation. Very simple. Okay. So the next one is 11. So we said where it should go. Okay, now we go back. Tell me where is there a violation? Is there a violation there?
There, yeah.
Yes.
Yes. Now, is it a single or a double rotation?
Left.
Single.
So
Double
single.
rotation,
We inserted 11.
Yeah, single.
double rotation.
It's a single rotation because we insert to the
Okay.
left of 15 and to the left of 13. Left, or right are always single. Okay, so simple rotations. Okay. And then we'll do 10, and then I think I will stop. Okay.
Yeah, so violation at 12. Yeah, violation.
Yes.
Single.
What is that? Single rotation.
Yeah, left.
Okay. 8, 9. And I think, yeah, I want to show the code.
Violation of 11.
No, it was
No.
2 minus, it was like 1. How about 13? No.
No.
Right? There? No.
No.
Actually, this is like a perfect tree, and then you have only 9.
Oh wait, no, isn't there a violation?
No. 3 minus 4 is minus 1.
Oh yeah,
If
yeah.
you look at every node, there is no difference of more than 1. Okay, so now we insert the last one. So let's go back. Is there a violation there?
Yeah.
Yeah, double rotation. Okay.
Left or right. Yeah.
Yes, that's it. Okay, so that's the basic idea. And continue with multiple examples. Now the question is, we have 10 minutes to see how we will implement that. Okay, so as we said, the only difference with respect to the binary says 3 is that you'll call it, and you have the code, you will call it AVL 3, of course. We have an AVL node that has a left and a right pointer, but it also stores the height. Okay, so when you create a new node, the height of this new node, because by assumption it's a leaf, goes to 0. Okay, and then every time, and if you want to return the height of the node, as you see here, we have a routine that tells you that the height of a node is either what is stored on the node, height underscore, or if the node is null, we said if the node is null, make the assumption that the height is -1. Okay, that's our assumption. Guy. Now you haven't said how we're going to update the heights, but yeah, this is how you have to store it. Question?
Oh, sorry. I'm sorry if you've been through this before, but why are you using a struct there instead of a class again?
You can use a class, but if you use a class, we have to add the word public, the keyword. Struct is the same as a class basically, but every parameter is public.
Thank you.
Okay. So you can access them directly. That's why you can say t height or t left or t right, because they are public, but they're public within the class basically, because the private, the AVL node is private. So if you're outside of the class, you cannot really access this node, but if you have functions within the class, you can access the node and left, right, etc. So now that's actually the insertion. Okay, so the insertion, there are 2 versions of insertion. I think this is a little bit easier to understand, even though, because it's in one chunk. So that's the insertion, and it's the same thing as before in the AVL tree. You insert in the binary tree, you insert under a node, you insert an X. Okay, and as in the binary tree, if you remember the insertion, if you have a null pointer, basically you are at the point of insertion, you just create a new AVL node, and you see here, you set the height to 0. That's the line here. So you create a new node and you set the height to 0. Okay, the same thing as in the binary says 3, but now you add the height. Now the situation is a little bit more difficult if you insert to the left or right. So if X is smaller than the node you are inserting at, so if X is smaller than the element, let's say your root has 2 and you insert 1, then you have to insert to the left of the root, or the left of, you have to insert X at the left subtree of T. Is this clear? So that's exactly the same thing as the binary tree. Okay, so I mean, we can see it here as on the fact. That's another way of saying it. That's another way of doing it. But basically, here you can see that you set to the left or you set to the right. Okay, so here that's the same thing. Oh, sorry. Okay. All right. So the difference here is that what will happen when do you check for violation? So basically, after insert x comma t left, for instance, when after you are here, after you're here, right? You check for violation. When will you come back there?
After you've inserted the actual node?
After you insert, you know, as you remember, when we saw the diagrams, you go to the root, to the leaf. This is the leaf, right? Sorry. You insert something at the leaf node, that's the leaf node, and then you come back, your equation comes back. So when you come back and you're at T and you come back, so when you're here, you're at T and you come back from your insertion, then you check whether you have a violation, okay? And you say, check whether the height of your left is smaller minus the height of the right is equals to or not. Okay, does it make any sense?
Yes.
Right. And now, why do you say equals to and do you say minus 2? Well, because you inserted to the left, okay? So basically, the thing that increased was the left. So basically, if there's a violation, is that the left became bigger than the right by 2. Okay, that's why you say 2 and you don't check for minus 2 over there. Is this clear? So if this is true, and if you're here and this is true, then what happens?
Where is here? I'm sorry.
Because I lost
Wait,
my
Can
pointer.
you repeat that whole why do we check if it's equal to 2?
Just a second. All right. I'm just okay, slideshow. All right. So here I say, when we say insert x t left, this is the here. Okay. It's just after under this. So after you come back from your insertion, so you insert to the left of t, and then you come back from your insertion, right? The recursion goes upwards, right? Does that make any sense?
Yeah, I guess so.
Yes. So basically now, because you said to the left, the only way to have violations because the left became greater than the right by 2, because before was right, it was correct. Okay, it was either the difference was either 1 or 0. So now if the difference is 2, then you have a problem. Okay. It was either minus 1, I'm sorry, 1 or 0. Now if it becomes 2, that's the case. You have a problem. Okay. So now the only thing you have to worry about is what type of rotation are you going to do. Okay, what type of rotation are you going to do? A left or a right rotation? So here you check whether it's a left rotation. Now, why do you know this is a single rotation? I'm sorry. Because if the x is smaller than the t left element, it means you insert to the left of the left. Okay, is this clear? You have your t, you insert to the left of the t, and then you check whether x is smaller than the left of the left. And then if it is, then you have a second rotation. Otherwise, you do a double rotation. That's it. And the other case is symmetric. Okay, are we okay with this? You can check the code in more detail if you want, but basically there's a raised hand question. No question. Okay, good.
Oh, no, I'm sorry. Yeah, I didn't hear that. Sorry. So could it be 2? Could it also be -2 or?
No, you can check for -2 if you want, but it will never be -2 over there. It would never be -2. If you check for -2, or if you say greater than 2, greater than
see.
1, or smaller than -1, it's fine, but it's redundant because it will never become a -2, because you increase the size of the left subtree, so it can never be -2. If you increase the size of the left subtree and you have a violation, it means that the left is bigger than the right by 2. Okay, that's why you don't check it. And at the end of this routine, it's very important. You update the height of T, right? The height of the node you're at. So as you go back, you update the height by just looking at the left and the right subtrees that have been updated before in the recursion, or not. Maybe, you know, they have not affected. They're not. So basically, the height of the T left and T right are already been calculated before. Okay. So when you're at T, you calculate the height at the end of this recursion, and then you will continue. So the heights are calculated as you go up. So that's the basic idea behind the. That's exactly the routine actually that we're using. We have an alternative insert that I'm not going to go through, but I don't know if you can understand in a better way. But the idea is the same as before. You do this binary search tree addition, but then when you come back, you do balance the T. So you have a separate routine that balances, but they're both equivalent. There's a little bit different code, but they're both equivalent. Okay. So the only thing you have to worry about now is how you're going to do the rotations. So we have a single rotation that we call rotate with left child. And let's try to do it here. K2 is the node that is where the single rotation is going to happen. And we know what we want to do. So we want to go from the diagram on the left to the diagram on the right. Okay. So how are we going to do it? What's the first step? What is K1 here?
I'm sorry, what's the question? What is K1?
Yes, in code. K2 is a pointer to the.
K1 is the left of, I mean,
K2.
is the node to the left of
Yes.
K2?
Yeah, so in code, so if you want to do a rotation, a left rotation, a left single rotation from K2, then K1 is to the left of K2. You know, you see that the way it is, and it's not now, right? It can be K1 be now. The reason it cannot be now is because you have a violation, which means that you insert it to the left of K1. Okay, if K1 was LAN, you wouldn't have a violation. Basically you wouldn't have the problem that you have. Okay, you insert it to the left of K2, you know that, and you increase the height, which means that K1 cannot be now. Anyway, okay, so now if you want to go to the situation on the right, what do you have to do? What is K1 left on the right?
X.
Which is the same thing as on the left.
Right.
Okay.
So you do nothing to that anyway?
What do you think?
You leave X, you leave K1 left pointing to X. Maybe I misunderstood your question.
Yes. Yes. Let's talk about K2 left. What
K2 left points to K1 right?
Yes. K2 left points to K1 right. Is this true?
Yeah.
Sorry for that. Are we done?
You have to swap K1 and K1 needs to be the parent of K2 now.
Right. So what is the left of K1? The K1 right?
K1 right should be K2.
Right. So by doing that, you have the situations you see on the right. Okay, you don't have to worry about the X and the Z because they are like to the right. Z is to the right of K2 before, it's to the right of K2 after, right? Now, the other thing you'll do, and you'll see it in the next slide, you update the heights of K1 and K2, which is very simple, okay? Updating the heights of K1 and K2. The only thing you do is that you look to the left and the right subtrees of K1 and K2, and then you just do it, okay? But you're not done. So I'm gonna show you the code in totality. Okay, this is exactly what we did before. K2 height, K1 height, you update the heights, but at the end you say K2 equals K1. Do you know why you do that? Or a question, I think we are over time, but I'm gonna continue because I have to finish this point. Do you know what we do the last K2 equals K1, assigned to K1?
To set the new root?
Hmm?
Or- no.
What will happen if you don't have K2 equals to K1?
Whatever's pointing to whatever's above K1 and K2.
Let's say you don't do. Let's say you don't do that. Yeah, whatever is above K1, above K2, where will it point to? Note that this is the situation here, right? So K2 has some pointer above it, okay? There is a node that points to K2. Where should the node point now?
K1.
K1, right?
But
The
you don't
node
have
that
to
was pointing
say,
to K2. The node that was pointing above should point to K1. Now, if you say K2 equals K1, what happens? See here, this is the interesting thing about the over here, we have the ampersand, all right? So basically, you change it. So what is K2 basically? K2, if you had a node here, T, let's say, what is K2? Is the left of T, okay? So basically, by saying K2 equals K1, what are you doing? The left of T is K1. Why? Because K2 is passed by reference, and essentially what you're doing, you're changing K2, which was the left of T, and the left of T becomes K1. So basically, it is very important to have that. K2 equals is assigned to K1. If you don't do it, and you can just, just for fun, you can just go to the code and just remove K2 equals K1 from rotate with the left child and see what will happen. Just check it, okay? All right, I think we stop here. Any questions?
I have a quick one about the struct. When you created a binary node, you didn't have a zero parameter constructor. Is that just there by default? So you didn't have to write it?
Okay. Let me go to this. I think I missed the slides here. Here you mean, right?
Yeah.
Actually, if you see the code, I don't think that in the code you call any zero parameter constructor for AVL node.
Well, what if you're creating just the root, the first node?
You have to pass it. You have to pass it with the arguments that you have.
Oh, it's just in null pointers for the left and right. Got it.
You have to pass null pointers, height 0, and comparable is basically the item. So basically, when you see here, this is the base case, and you pass it like that. So you don't really call the zero parameter constructor.
Awesome, thanks.
Yeah. So you don't have it. All right. Okay, everybody. Any other question? Think I'll see you next time. And you know, do the homework, and we'll take it from there. Bye, bye.
Okay.